your angle's bigger, that technically your projection's going in the opposite direction. So it's okay to have a negative component, it means they're pointing in the opposite directions. Trying to figure out if I guess we could do the next part of 20. I think I'll draw. I think I won't draw them up there because they're short little vectors. Okay, so you guys, in this problem, I guess one thing to point out is the I, the J, and the K. In our class, those are called the standard component vectors. So I know this was on your quiz. In linear algebra, it's just called the basis vectors. Okay, just different names for the same thing. So 1, 0, 0 is I, 0, 1, 0 is J, 0, 0, 1 is K. If you're asked for them, it's okay to list them like this, it's okay to list them like this. What's important is you know that these are the same thing, and these are the same thing, and these are the same thing. But if somebody asks you for the standard component vectors and you list these, that's correct. If you just say IJK, that's also correct. So vector A, if you add I and J and K together, you get the vector 1, 1, 1. And vector B, if we take I and we subtract J, you're going to get 1 minus 1, and then if we add K, we'll get positive 1. So graphing those,
Plus yes.
okay, here's vector A, and then vector B is 1, but Y is negative, and Z is positive. Yeah, it's not gonna show up real well in our little drawing.
Put that at 90 degree.
Yeah. Okay, so let's follow the same directions. We're trying to find the component of, and we're doing B onto A. So we're projecting B onto A. So I'm going to take, again, where this all comes from, you take the length. Okay, well first dot, you're going to dot your two vectors. So 1 times 1, so A dotted with B, that's my numerator. So 1 times 1 is 1. 1 times negative 1 is negative 1. And 1 times 1 is 1. So their dot product ends up just being 1 in the numerator, okay? Then in the denominator should be the length of the vector you're projecting onto. So I'm projecting onto A, its length is going to be the square root of 3, which happens to be the same as the other vector. Okay, so their component, the component of the one projected onto the other is 1 over the square root of 3, which actually means they're not 90, because if I had dotted them, I would have gotten 0 instead of. Okay, so that's the length of the one vector projected onto the other. If you then turn it into if you actually find the projection, which is a vector itself, then it'll be 1 over the square root of 3 times the unit vector in the direction of the vector you're projecting onto. So I'm projecting onto A. So this as a unit vector is going to be 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. And again, it's okay to leave it like that. In this case, the square roots of 3 clean up nicely, so you get 1/3, 1/3, 1/3. Okay, so if you cast B onto A, the shadow vector that gets cast onto A is this vector here. The length of it is 1 over the square root of 3. Okay. So this vector has that as length. Right, and I'm trying to think what section that was in, 'cause I know kind of, I think it's section 12. Let me see. So if you want more pictures and you want more examples, yeah, section 12.3 is where you'll find this discussion. Okay, so again, on your Blackboard side, I've listed practice problems from the section, so 12.3 is where you'll find more practice. So it's in like the 30, 39, 40, 41. That section is having you practice those, okay? All right, we kind of need to keep moving forward. I will post, I know there's probably about 6 problems we did not do in class on this packet, so I will post those on Blackboard. So I would suggest you try to read through the rest of the ones we didn't do and look at that. I will post it. I gave you guys a new packet, so if you want to get out the new packet.